Alrighty. I think I've already said it, but good morning, class.
Good morning.
Thank you. Okay. We're going to go ahead and finish up this section today. Section 2.6. 2.6? Yes, 2.6. Graphs of rational functions. We finished up yesterday by analyzing the graph of a rational function. We're going to get to do that again with this one. And the one we did yesterday when we finished up, I don't know where my copy of the notes went, but the graph looked like that. And there was a bunch of analysis on the bottom, but this was from my other class. But anyway, it looked like that. So we're going to do the same thing with this one. Just going to be a different looking graph, that's all. But because we are going to have to do some analysis, leave some space. I'm going to try to, basically half the space I have for this question is going to be analysis. So don't write too large. The first job that you're going to have when trying to graph and analyze a rational function is factor anything that you can factor. Well, the numerator has a GCF, so I'm going to go ahead and factor off that GCF. And now we can easily see that both the numerator and the denominator have a difference of two squares in them. They can both be factored into a pair of conjugates, a plus b, a minus b. So we have 2 times x plus 1 times x minus 1 over x plus 2 times x minus 2. There it is. Nothing cancels out, so we don't have any removable discontinuities. And I still have 2 values for x. That would allow me to divide by 0. So I have 2 vertical asymptotes. I'm not going to write out vertical asymptotes. I'm too lazy. I'm just going to write VA. You will not do that on your AP Precalc exam. You'll write the words to make sure that you get full credit. But we have a vertical asymptote at x equals -2 and another one at x equals +2. Now, let's talk about end behavior asymptotes. If you can recall back to 2 lessons ago, I put a star next to this stuff, and it specifically said, if the numerator has a smaller degree, y equals 0, automatically horizontal asymptote. If they have the same degree, then you do have a horizontal asymptote, and it's found by dividing the leading coefficients. That is the situation that we have here, because both the numerator and the denominator are a degree 2 polynomial. To find my horizontal asymptote, all I need to do is divide the leading coefficients. And the leading coefficient on the bottom is a 1. So my horizontal asymptote, which again, you'll write the words when you take your actual AP exam, y equals 2 over 1, which is just y equals 2. A lot of 2's on that paper. That's just a coincidence that the horizontal asymptote and the vertical asymptote have the same value. 100% coincidental. Okay so far? Awesome. Let's track down intercepts. The x-intercepts. If you're on the x-axis, then it's known that y is 0 for all graphs. And the only way that this y value could be a 0 is if this fraction had a value of 0. And the only way that a fraction can have a value of 0 is if the top equals 0. The numerator has to equal 0. So we figure out what makes the numerator equal 0, and we know where our graph crosses the x-axis. So we look over here because it's factored, and we can see there are 2 numbers that make the numerator equal 0. X equals -1 and x equals +1. I heard a question in the room. Zero divided by any number other than 0 is automatically 0. And numbers divided by 0 is, you can't do that. Not allowed. Because we don't know how many times a thing of size nothing can fit into something with size. Alrighty. The other intercept, excuse me, would be a y-intercept if we have one. And the only way that you're on the y-axis is if x equals 0. So if you want to know the y-intercept, this is true for all graphs at all, you're just going to let x equal 0. Mark, what's up?
For the x-intercept, why wouldn't 2 equal 0? So 0
Because 2 doesn't equal 0. Because you can't, so if basically you're saying what makes each piece equal 0, but the only thing that could make it equal 0 is an x value. And since 2 doesn't have an x value, you're saying, oh, what makes 2 equal 0? Nothing. All right, nothing's going on here. Now, if it's a 2x, then you're saying what makes 2x equal 0? Then x equals 0 works. Okay? So you're just looking for where there's x's, because those are the only things that can be made to equal 0. For our y-intercept, we're just going to allow our x value to be 0. And you plug in a 0 here, you get 2 times 0, 0. You put a 0 here, you get 1 times 0, 0. Basically, what you're going to get is negative 2 over negative 4. So f of 0 is negative 2 over negative 4, which is positive 1/2. So we have a graph with 3 asymptotes and actually 3 intercepts. Interesting, that's coincidental. That's enough to start sketching the graph. Please don't draw it too large. Remember, we do have to do a lot of analysis. And a piece of analysis that I forgot to do with yesterday's concavity. I completely forgot to do it with yesterday's analysis in that last question. So we'll do it on today's. I'm going to remind you what it means for something to be an asymptote. It's a line that we approach. We will get infinitely close to it. That's all it means to be an asymptote. It's something that we will get infinitely close to. I didn't say that part. An asymptote is something that we get infinitely close to. Now, occasionally, you're going to have graphs that go right through their horizontal asymptote. And that's fine, because it's actually called an end behavior asymptote. It describes what's going on at the endings. It does not describe what's going on at 0. However, vertical asymptotes, because they are problems with our domain, we can't cross those. It's not possible, because you can't evaluate when x is negative 2. You can't evaluate when x equals positive 2, because those are places that break our function. So we'll just remind ourselves what it means to be an asymptote. It's something we're going to get close to. Cool. What do we know? All 3 intercepts. Negative 1, positive 1, and y equals 1/2. Well, look here in the middle. The only way that I'm getting infinitely close to these 2 vertical asymptotes, but going through all 3 of these points, is to draw something that looks like a quadratic. And to figure out what's going on in the other zones, we need a candidate from each zone. So I could pull the number 3, and I could pull the number negative 3. And something that should make you pretty happy is that if you look over here, everywhere there's an exponent of 2 on it. That means it doesn't matter if x is positive or negative. I'm going to get the exact same y value. This is an even function. It's symmetric over the y-axis. So to really drive home this point, I'm going to plug in 3 and negative 3 at the exact same time. Because it won't matter. There. So yeah, square that positive 3, square that negative 3, it doesn't matter. You're going to get 9 for both of them. So this is 2 times 9, which is 18, and 18 minus 2, which is 16. And 9 minus 4 is 5. Now look, I don't really actually care what, is that a question? Oh, just scratching his head. Okay. I don't really care what the value of this is. What I really care about is above 2 or below 2. Is this number bigger than 2 or less than 2? Bigger than 2. That means my curve in these candidate zones exists above the y value of 2, forcing me to have an image like this. Ta-da! Light work, right? Oh, 2 hands went up. Charlie? Oh, doesn't really matter.
Okay. How do you know if it's like if it matters the value or not?
Well, I mean, it always. You mean when would I care what that number actually is?
Instead of just doing positive and negative.
Well, and I didn't just do positive and negative. I did specifically above 2 or below 2.
Yeah, but like yesterday we did if it equals a positive or not.
Well, that was because I was actually asking above 0 or below 0.
Oh, because there was a horizontal.
And then here, we had to be really careful, though, because we were talking about above or below a line, which was why I said, okay, well, we know this is y equals x. So at this x value of -4, I have a y value of -4. So then I was checking above or below -4. Because, again, I was saying above or below this line. It just wasn't horizontal. So I had to find its actual y value at that asymptote. But for this one, the y value is always 0. And for this one of the asymptote, the y value is always 2. So it was just easier. Adi, what's up? Okay, cool. 2 birds, 1 stone. I like that. Because screw birds, that's why. Alrighty, now, let's go ahead and do the full analysis. Unbounded, that's part of the analysis. And we've already mentioned that it's an even function. That's part of the analysis. You don't have to write that stuff, I'm just saying it. Here's what we're going to do. Let's talk about positive and negative. Positive and negative means above the x-axis and below the x-axis. So when is it above the x-axis? This whole piece here is above the x-axis. So from -infinity up to the number -2. There's more. This piece right here is above the x-axis between -1 and +1. And then this piece over here, after x equals 2, is above the x-axis. So that's where I have positive y values. These are all the x zones that give me positive y values. That's what it means to say positive. And the negative y values are going to come from this little stick and this little stick. So from x equals -2 to x equals -1. And then again from +1 to +2. On those x values, I will get negative y values. Time for increasing, decreasing. I'm sorry? Oh. Increasing, decreasing. Looking at our roller coaster. On this part of the track, going from left to right, my car is going up. Whee! So that is increasing. From -infinity up to x equals -2. I cannot put a bracket on x equals -2 because the graph doesn't exist there. It's also increasing on the left side of this downwards facing curve. So from -2 up to the number 0. Now at x equals 0, I can use a bracket because at x equals 0, I'm going to start decreasing. So this point is a change between increasing and decreasing. So from 0 to 2. Have to hop over 2 because my graph doesn't exist there, but then once again after 2 for all infinity. How about concavity? On your actual AP exam, please write concave up, concave down. I'm going to be lazy and use CC. So concave up means curving up. We don't say from left to right though. We just talk about curving up. And I had an epiphany during second period as a way to describe concavity. Let's say you were strong like bull. You're a strong man, and you're going to take this horizontal bar and you're going to bend it. If this side bends up or this side bends up, then that's concave up. But from horizontal, if you're strongman and you're holding one side still and you bend this side down, or you were holding this side and you bend this side down, this is concave down. So imagine you're holding a piece of rebar or something and you're trying to bend it. So you're looking at my rebar up here and asking yourself, where is it concave up? Where does it bend up away from the horizontal? Those two. Both of these bend up away from the horizontal. So from negative infinity to negative 2, and also from 2 to infinity, but the bar bends downwards from the horizontal between my asymptotes. Positive, negative, increasing, decreasing, concave up, concave down, boundedness, symmetry. That's pretty much the full McGillicuddy. Now we're just going to do limit behavior. The limit, as x approaches negative infinity, that means going out to the far left of my graph, actually is going to get me the exact same result as when I go to the far right. Because both endings approach the same y value, 2. And this is the y value of 2. I'm only writing that in a note so you don't think it's the x value of 2. It's this line. Both ends approach that line. Now all I can do is describe my limit behavior on these two sides of each of my asymptotes. So I've got a left-hand behavior, a right-hand behavior, a left-hand behavior, a right-hand behavior. So let's go to x equals negative 2. The limit as x approaches negative 2 from the left side of negative 2. So you go to the graph, you look at negative 2, you go immediately to its left and ask yourself, what are your y values heading towards? Well, they're pointing up. So infinity. Now we have to go to the right side of negative 2. You go to negative 2, go immediately to its right, and ask yourself what the y values are doing. Oh, they're shooting down. Negative infinity. We'll pull off the same trick at x equals 2, and we'll be finished with this question. So go to 2, but just go a little bit to the left of it. Go to 2, go to the left, and say, what's y doing? Ah, shooting down. Negative infinity. Still hanging out at x equals 2, but now we're going to go just to the right of it and ask ourselves what our y values are doing. Go just to the right of it there, woo, going up to positive infinity. Oh, that's an analysis. You see that stuff? My golly. That's a lot of understanding. A lot of knowledge. You guys want to ask me anything about any of that? I mean, there's a lot going on here. Happy to answer questions. Is that a question or is this just another stretch? Okay. What do you mean?
With the exponent being greater, the exponent being equal to, and the exponent being larger, right? They're not going to see any type of difference.
Well, let me ask you. If one is bigger than the other, one is smaller than the other, or they're equal, what other options would there be? I mean, like, that's it. You described all the ways you can compare two numbers. They're equal or they're not equal. So no, we've already seen those are the only three. Top heavy, bottom heavy, and equal. And this one they were equal. Cool beans? Hmm? The blue or the black? Okay. Yes, because it's the y value. Whenever we're talking about these limits as x approaches of f of x, we're saying as x goes this way, my y values are getting closer to 2. Because it's approaching the asymptote. 2 horizontal asymptotes? 2 horizontal asymptotes, they can occur, but I don't think I can make them occur with rational functions. They can occur with other things, and then you wouldn't be able to set them equal to each other. So you would have like one as it goes to negative infinity, you'd have one as it goes to positive infinity. Yes? Yes, this was the horizontal asymptote because I just wanted to know where my y values above or below that line. Because if we had said, let's just say I got like a number of 1 or 1.5 or something, then this curve would have been drawn here below the value of 2. Yes, so this is a y value. And this is a y value. You know, f of, when you say f of, you're saying y value when. Okay. These are good questions. This last one. Typically, you're going to factor everything that's possible to be factored. Well, guess what? That doesn't factor. It just doesn't. I mean, that's not to say it doesn't have a solution. I mean, it obviously has a solution because it's a cubic. And all odd degree polynomials have to cross the x-axis. They don't have a choice. It doesn't factor by grouping. It just doesn't factor. Because its one solution is irrational. So it doesn't factor. Because it only has one solution, and that one solution is irrational. So when you have a single irrational solution for a polynomial, there's no way to factor it. There's nothing we could do with it. The only way to figure out the solution for this is to grab a graphing technology and ask the graphing technology to tell you where it crosses. Using second trace intersect. Well, I mean, you mean, should you be able to recognize if it's factorable or not? I mean, you should be able to recognize it because the only thing that's possible is factor by grouping, right? So what's the GCF of the, don't look at the bottom. What's the GCF of the first group? X squared leaving behind an x minus 3. Can this leave behind an x minus 3? No, it can't. Therefore, factoring by grouping doesn't work. And that's the only way you'll ever be able to factor 4 terms is by grouping. So if it doesn't factor by grouping, and you should be able to see it fast if it does or doesn't, then no. So what do we do if we can't factor it? Well, let's identify at least our asymptotes. I can see, oh, by the way, since this isn't going to cross off the bottom, I know there's no removable discontinuities. Because this doesn't factor. So there's no way that's one of its factors. Anywho, I have a vertical asymptote at whatever makes the bottom equal 0. X equals positive 1 is a vertical asymptote. This is a top-heavy function, though. The degree of the numerator is bigger than the degree of the denominator. When you have top-heavy, the only way to find your in-behavior asymptote is long division. There. Time for long division. We are trying to make an x become an x to the third. I'm going to need an x squared. Take your x squared and distribute it to x plus 1. You will get x to the third plus x squared. Oops. I wrote +1, not -1 by accident. Sorry about that. Minus x squared. Well, that's going to make this look ugly. This says minus a negative. That means plus. So -3 plus 1 is -2. Drop down that 3x. We're trying to make an x look like a -2x squared. I need a -2x. Distribute your -2x. You get -2x squared plus 2x. Where'd you go, red pen? There it is. Subtracting straight down. Minus negative is plus, so that's 0. 3 minus 2 is 1. Drop down the +1. And lastly, you need an x to become an x. +1. The rest of this question doesn't matter, but just for, I don't know, continuity's sake, 1 times x is x, 1 times -1 is -1. Subtracting straight down gets me a remainder, which we already expected to see a remainder because we knew this didn't factor, so there's no way that this was going to go without a fight. It's going to leave behind a remainder, excuse me, of 2. So we go plus 2 over x minus 1. But if you recall, yesterday we talked about how when you have to do the long division, the remainder portion of the in behavior asymptote will always go to 0 as x gets bigger, 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 because the remainder portion will always be bottom heavy. So this, that you can't see, this is going to go to 0, which tells us our in behavior asymptote is y equals x squared minus 2x plus 1. A quadratic in behavior asymptote. And what's really neat about this quadratic in behavior asymptote is that it happens to be a perfect square trinomial. It factors into x minus 1 squared. The two numbers that multiply to 1 and add to -2 are -1 and -1. Why do we care? Because we need to be able to graph this in behavior asymptote. The vertex of this asymptote will be at 1, 0 because it's in vertex form. We don't have the ability to find 1, 0 is the vertex of this quadratic because 1 makes the inset equal 0 and there's no vertical shift on the outside. We don't have the ability to factor our numerator, which means unless we use technology, we actually can't figure out what the x-intercept is. We don't know what makes the top of this fraction equal 0. I mean, it definitely has a value because it's cubic and all cubics cross the x-axis. But we can still find the y-intercept. Because for all graphs, if you want to know where your graph is going to cross the y-axis, you just use x equals 0. Let's see, f of 0, what are we going to get? I'm going to get 0, 0, 0 plus 1 over 0 minus 1. Oh, my y-intercept is at -1. I think we're ready to go. There's x equals 1 with its vertical asymptote. Oh, x equals 1, that's also the vertex of my in behavior asymptote. Looks like a upsilon. Anyway, got our zones. 1, 2, 3, 4. The only other thing that we know is that the graph crosses the y-axis at -1. Okay, well that's helpful because, check that out. The only way that I can go through this point and get infinitely close to this line and this line is if my graph does something like this.
How did we get those, like, the curved parabola?
This?
Okay.
It's just a quadratic. It's a quadratic quadratic in behavior asymptote. So you could either factor it and know that its vertex is at 1, 0, or you could do x equals negative b over 2a and get that your vertex occurs at positive 2 over 2, which is 1. You need to plug 1 in. Now remember when we talked about it earlier, this period, this right here, we had to figure out if we were above or below this dot by looking at its y value. We're going to have to do the same thing on the right side of the vertical asymptote. Oops. Because I don't know if I'm above or below the curved asymptote. So either my graph does this and hugs the outside, or my graph does this and stays on the inside, and we're not sure. So what we do is we track down a candidate y value, x value, excuse me, of 2. But on my asymptote, the coordinate there, that is at 2 comma, and you could just literally come up here and drop x equals 2 into here, and you get 2 minus 1, excuse me, which is 1. 1 squared is 1. So right here, my y value is 1 for my asymptote. Comfortable with that idea and how I did that? I'm going to find the actual y value of my graph at x equals 2. And all I care about was above y equals 1 or below y equals 1. Let's find out. F of 2. Yeah, above the curved asymptote or below the curved asymptote. So I have to do 2 cubed minus 3 times 2 squared plus 3 times 2 plus 1 over 2 minus 1. Good news, everyone. When you plug in x equals 2, the denominator is just 1. Eight minus 12, that's negative 4. And negative 4 plus 6 plus 1, negative 4 plus 7, that's 3. And that value is above the y value of 1 that I had right there. So since the actual, oops, I forgot to drop a 2 right there. Since the actual y value of my curve is above the y value of my asymptote, the curve looks like this. So, analysis. Well, we're not going to talk about positive, negative, because I would have to use technology to figure out where my x-intercept is. We're not going to talk about increasing, decreasing, because I'd have to use technology to figure out where this swaps between increasing and decreasing. We're not going to talk about concavity, because there's a change in concavity somewhere over here, and I would have to use calculus to figure out where that is. So the only other thing we could do is use limit notation at the asymptotes. Well, look, the limit as x approaches negative infinity, or the limit as x approaches positive infinity of f of x is positive infinity, there. And I think we can all see that on the left of this we go down, and on the right of this we go up. So I would say that's enough analysis for that one. Unless you have questions for me, that's what we're going to call it. Yep.
So it's more about the remainder and why it goes to 0. I'm still like not really getting that.
Why does the remainder go to 0? Well, where's my graphing calculator? The remainder is 2 over x minus 1, right? Okay. 2, actually, alpha y equals 2 over x minus 1. As x gets larger and larger and larger, look where that y value is crashing towards. It's going to 0. So the remainder will always go to 0 because it's always going to be bottom heavy. Then the dividend is my in-behavior asymptote. The remainder will always go to 0. So when you're doing in-behavior asymptotes, the remainder always goes to 0. So the dividend is literally the in-behavior asymptote. Well, I mean, I didn't ignore it. It's just that it means less and less and less as x goes to 0. Yeah, kind of like an in-behavior model. Well, okay, so if I didn't have the minus 3x squared and the plus 3x, then it would have been exactly x to the third over x. Because these numbers don't do anything. But it's not x to the third over x anymore because there's x's there now. So it ends up going to x squared minus 2x plus 1. And the only way to have known that was using the long division. Now I'm going to graph this. Let's see it. X squared minus 2x plus 1 plus alpha y equals 2 over x minus 1. Wasn't that interesting? You don't see it? That's basically what my graph was. That's the in-behavior asymptote if I include the 2 over x minus 1. That shouldn't surprise anybody. Because if you leave that there, it's exactly the same thing as if you had just said this over this. That's why that's our graph. But if you discount this part, what you get is the in-behavior asymptote. And it just gets really close to the in-behavior asymptote on the left and the right side. Okay? Welcome. Boink. All right. That was fun.